In this video, we'll be continuing to look at alkenes. We'll be focusing on bonding and structure, as well as physical and, very briefly, chemical properties of alkenes. As we think about the structure of alkenes, we need to focus on the hybridization of our alkene carbons. So each of these carbons is connected to 3 groups. That means they will be sp2 hybridized. So if we focus on a single carbon, it will have 3 sp2 hybridized orbitals. And so one might be going in this direction, one is going back behind, and one is coming forward. So these 3 are in a plane, and that plane is perpendicular to the plane of the screen. In addition to those 3 sp2 orbitals, we also have an unchanged p orbital. Now, if we draw in our second carbon, here is the sp2, sp2, and sp2 orbital, and the p orbital. So what we can see is that here we have overlap of a carbon sp2 with a carbon sp2. That gives us a sigma bond. Over here, these sp2 orbitals would be overlapped with hydrogens. So that will also give us sigma bonds created by the overlap of a carbon sp2 with a hydrogen s orbital. But we also have our p orbitals that are parallel to each other, and they can be overlapped with each other. And so that gives us a pi bond created by the overlap of a carbon p with another carbon p. Now, if we focus on this molecule, but we're looking at the side view, let's say that here is our red carbon, and then we're putting our black carbon right in front of it. The carbon sp2 orbitals overlap to give electron density that is along the axis that joins those 2 atoms. So that is our sigma bond. And remember, we have free rotation around single bonds because that doesn't interfere with the bonding. However, if we're still looking at this from the side, our p orbitals are going to give us pi bonds, which have electron density above the axis that joins the atoms and below the axis that joins the atoms. So looking at this from the side view, we're going to have a cloud of electron density up here and a cloud of electron density down here. And remember that here we're actually looking at, let's say this is the cloud of the red carbon in back and the cloud from the black carbon in front. The cloud of the red carbon in back, and then the cloud of the black carbon in front. So these would be the resulting clouds of electron density from our pi bond. Why did I just give you that reminder about sigma bonds and having free rotation? Well, let's think about trying to rotate around a double bond. If we were to take this atom and rotate it around, then this sigma bond would not be affected. But what would happen, let's say here is our red carbon, and now I'm going to change the colors of the p orbitals. So let's say this is the electron cloud from the p orbitals corresponding to our original red carbon. Now, if we rotated the other carbon so that it's now facing this way, those p orbitals are going to look like this. So this p orbital is no longer perpendicular to this p orbital, so we would have to break a pi bond to be able to rotate around this bond. So while we can rotate with a single bond, we cannot rotate with a double bond because it would break the pi bond. And we're going to see an important consequence of that in just a moment. Now let's compare a little bit more about the structure of an alkane and an alkene. Looking at our carbon-carbon bond, when we have a carbon sp3 overlap with the carbon sp3, this has a bond length of 153 picometers. Here, where we have a carbon sp2 overlap with the carbon sp2 and a CP, here we have a bond length of 134 picometers. So a double bond is shorter and stronger than a single bond. A pi bond is not the same strength as a sigma bond, so a double bond is not twice as strong as a single bond, but it's definitely stronger. Another difference I'd like to point out, looking at the carbon-hydrogen bond, in an alkane where we have an sp3 hybridized carbon, this has a bond length of 111 picometers, and over here, this is 110 picometers. So you know that I always draw my sp3 orbitals the exact same way as my sp2, the exact same way as my sp. If we were to be more precise in our representation, maybe this would be an sp3 orbital, and this would be an sp2 orbital. Here we've got 75% p, 25% s character, and so the sp3 orbital is going to be further away from the nucleus. Here we've got 33%, 66%, so these electrons will be held a little bit closer to the nucleus, more like the s character. And so because the orbitals are a little bit closer to the nucleus, that means that the bond lengths are going to be a little bit shorter as well. Now let's think about some of the consequences of sp2 hybridization and having a double bond. If we were to consider isomers of butene, C4H8, we could have this where we have a CH2 double bonded to a CH, CH2, CH3. We could have a CH3 connected to our CH, double bonded to a CH, connected to a CH3, or we could have CH2 double bonded to a C, which is connected to two CH3 groups. Now, the relationship between these, they all have different connectivity, so these are constitutional isomers. They have different connectivity. But we need to be a little bit more specific when we talk about this alkene, because if we draw our alkene, the carbon on the left is connected to a methyl group and a hydrogen. The carbon on the right is connected to a methyl group and a hydrogen. Once again, the carbon on the left is connected to a methyl group and a hydrogen. The carbon on the right is connected to a methyl group and a hydrogen. Now these compounds have the same connectivity because the alkene carbon is connected to the other alkene carbon, a methyl group, and a hydrogen, just like this one is. But they have a different arrangement in space. We talked about different arrangement in space when we were looking at conformations, but remember, conformations can be interconverted. But I just told you that we cannot rotate around a double bond, so that means that these compounds cannot be interconverted. Therefore, they are not different conformations of the same compound, they are different compounds that can't be interconverted. But at the same time, they do have a different arrangement in space, so that means these are stereoisomers of each other. Stereoisomers. Just as we saw with cycloalkanes, if we have two substituents, if both substituents are on the same face of the ring, that's called cis. If the substituents are on opposite faces of the ring, that's called trans. We can use the same terms for alkenes. Here we have our methyl groups on the same face of the alkene. So this one is cis. Here we have our methyl groups on opposite faces. This one's on the top, this one's on the bottom. So this would be trans. So they're stereoisomers. Remember, we also talked about enantiomers, which are non-superimposable mirror image isomers, so a subset of stereoisomers. These are not mirror images of each other, so they're not enantiomers. Instead, they are diastereomers. So, because we do not have free rotation around a double bond, alkenes can potentially exist as a pair of diastereomers, so as cis and trans. Next, let's consider the relative stability of alkenes. We can use the heat of combustion to compare all of these isomers. These all have the molecular formula C5H10, but most of them have different connectivity, and then these have the same connectivity but different arrangement in space, so these are diastereomers. Several are constitutional isomers, and then these are stereoisomers. Looking at the heat of combustion in kilojoules per mole, this can, if we think about the combustion, because all of these are C5H10, they will combine with oxygen to form CO2 plus water. We can balance this. We need 5 CO2s. We can balance this equation because we have 5 carbons on the left. We need to have 5 carbons on the right. We have 10 hydrogens on the left. So let's try 5 water molecules. This is going to give us a fraction. So instead, let's use 2 of these to give 10 CO2 and 10 water. So now we have 20 oxygens plus 10 oxygens. So this would be 15 oxygens over here. See, we're not allowed to forget everything from general chemistry. We do have to remember how to balance an equation. But the important thing about this is that any of these isomers are going to result in the exact same products. So if we're thinking about an energy diagram, and this is our starting material, and this is our product, so this would be the delta H. Now, all of these different starting materials have the same products, so by using the delta H, we can figure out the starting point of the starting material. So let me erase this, and then let's start filling in some of these values. If we look for the largest value, this is here 3376. Let's say this is our product, and let's put this all the way across. So here we have a difference of 3376, and that corresponds to this compound. Next, we have 3369. So this is 3369, and here we are looking at the cis compound. Next would be 3365, so just a little bit lower in energy. That is for the trans compound. Next, 3362. And that is this one. And then finally, the most stable one, 3356. That is this one that is tri-substituted. So because they all end at the same energy, because they end with the same products, the different delta H tells us the starting point. So we can see the difference in energy of these alkenes. Here we have our alkene carbons with only one alkyl substituent. This compound would be called monosubstituted. So hydrogen, 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 that doesn't count. An alkyl group, that counts as a substituent. So this one has one alkyl substituent, monosubstituted. These have two alkyl substituents, two sp2, so these are all di-substituted. This one has 3 alkyl substituents and only 1 hydrogen connected to the alkene carbon, so this one is tri-substituted. So one thing that we can see in general is that the more substituted, the more stable the alkene is. That doesn't get into the nuances of the differences between here, but the monosubstituted is the highest energy, the disubstituted are in the middle, and the trisubstituted is the lowest energy. So in terms of the relative stability of alkenes, monosubstituted alkenes are less stable than disubstituted, which are less stable than trisubstituted, and then trisubstituted would be less stable than tetrasubstituted. First of all, why is there a difference between the mono, di, tri, and tetra substituted? Well, we know that a carbon-carbon double bond is stronger than a carbon-carbon single bond. But what's also true is that a carbon sp2 to carbon sp3 compared to a carbon sp3, this is going to be stronger. So the more substituted, the more CsP2, CsP3 bonds there are. There's also a molecular orbital theory approach that we could use to explain this difference, and there is a hyperconjugation approach that we could use to explain this general difference. If you are really curious and you want to dig deeper into why, let me know and we can find that information. But in general, I want you to be familiar with this general trend. Monosubstituted are less stable than disubstituted, are less stable than tri, are less stable than tetra-substituted alkenes. Within the disubstituted, don't worry about this one compared to these, but if we're looking at cis compared to trans, the difference here is about sterics. With cis, these groups are on the same side. There could be just a little bit of crowding, and that crowding doesn't occur when these groups are across from each other. Now, all of this difference in stability, we're going to see how this plays a role in product distribution when we are looking at reactions to prepare alkenes. Next, let's consider the physical properties of alkenes. And remember that physical properties are determined by intermolecular forces. In the case of alkenes, because we just have hydrogen and carbon, these have very similar electronegativities, so these are going to be held together by induced dipole interactions, or London dispersion forces. That means that things like boiling point, melting point, these are going to be pretty low, very much like alkanes. Water solubility, this is also going to be very low. But let's take a look at a difference here. So here we have trans 2-butene. We're getting a little preview of naming. And here we have cis 2-butene. And for trans 2-butene, the boiling point is 1 degree Celsius. For cis 2-butene, the boiling point is 3.7 degrees Celsius. Even though it's a small difference, the fact that it's a difference is important. So is it because of intermolecular forces? Is it because of the way it packs? Is it because of surface area? Well, it was found that there's actually a difference in the dipole. For trans 2-butene, the dipole moment is 0, but for cis 2-butene, the dipole moment is 0.3. Again, very small difference, but the fact that there's a difference, that's something. So if you notice here, our methyl groups are across from each other. Here our methyl groups are on the same side. The only way that the cis could have a dipole moment and trans doesn't is if there is a difference in electronegativity between sp2CH and sp3CH. So a carbon that is sp3 hybridized and a carbon that is sp2 hybridized have slightly different electronegativities. But the question I have for you is, which one is more electronegative? If sp2 is more electronegative than sp3, then in the case of trans, we would have the bond dipoles going like this, and they would cancel. In the case of cis, we would have the bond dipoles going like this, and they would add up to give a molecular dipole in this direction. But if sp3 is more electronegative than sp2, then these bond dipoles would be going in this direction, and they would still cancel. But over here, the bond dipoles would be going in this direction, so they would add up to give a molecular dipole like this. So this doesn't help us, right? We can't tell just by looking at this information whether sp2 is more electronegative than sp3 or if sp3 is more electronegative than sp2. Now, this isn't something that I'm going to test you on, but I'm sure I can tell you are just so curious and you need to know which one is more electronegative. Well, let's look at some more experimental evidence. If we have ethylene itself, we just have the carbon-connected hydrogens, and that has a dipole moment of 0 dBi. D for dBi is the units. If we have chlorine connected to the alkene, then this gives us a dipole moment of 1.4. We know that chlorine is more electronegative than carbon, so we know that that bond dipole is going in that direction. When we have a methyl group, we measure a dipole moment of 0.3, but we don't know which way, if our bond dipole is pointing in this direction or in this direction. But here we have a methyl group and a chlorine, and they're pointing in opposite directions. And in this case, we measure a dipole moment of 1.7. So once again, we know that chlorine is more electronegative, but we still don't know about this bond. Well, let's think about this. So if sp3 was more electronegative than sp2, then we know that chlorine is pulling away electron density from the carbon, and if sp3 was more electronegative than sp2, then this carbon would be pulling away electron density as well. Not as much as chlorine, but it would subtract from this bond dipole. It would partially cancel it. And so we would expect then to have a dipole moment less than 1.4, which is what's observed when there's a chlorine connected to the alkene. On the other hand, if sp2 is more electronegative than sp3, then when we're looking at this, then we know that chlorine is pulling away. If sp2 is more electronegative than sp3, then this bond dipole would be going in this direction. And so here we would expect that this dipole would add just a little bit to this dipole. And so we would expect to see a dipole moment greater than 1.4. That's what we observe, and so this must be the case. So sp2 hybridized carbons are just slightly more electronegative than sp3 hybridized carbons. Finally, let's think briefly about chemical properties of alkenes. With chemical properties, we're just talking about reactivity. What kinds of reactions is an alkene likely to undergo? Because we have a double bond, so in addition to our sigma bond, we have a pi bond. But think about what this means. On all of these sigma bonds, we have this electron density along the axis that joins the different atoms. But in addition, when we have a pi bond, you know what, I need to rewrite this. So here's our hydrogen going back. So I'm just taking this molecule and turning it on its side. So with all of the sigma bonds, we have electron density that goes right along these areas. But with a pi bond, we have electron density above and below the axis that joins the carbons. So we really just have this electron density that is very exposed or accessible to be able to react with something. Now, we've just spent a lot of time talking about nucleophiles. Well, we can have something that has a lone pair of electrons and it can share its electron density with an electrophile. And part of what makes a nucleophile reactive is if it has a lone pair of electrons that's very exposed, very accessible, very ready to react with an electrophile. With a pi bond, because we have this exposed electron density, these electrons also are able to be donated to an electrophile. So we will be looking at examples of alkene reactions where the alkene donates electrons to an electrophile, so it's kind of acting like a nucleophile.